Good morning. I'm Professor CHASNOV, Jeffrey CHASNOV, in the math department. I've been teaching here for 20 years now. But I'm afraid I never learned Chinese. Very sad. But the lectures here are in English, everybody knows, right? So I'm supposed to be talking about mathematical biology. So rather than give you an overview of the whole area, I want to just concentrate on some small topic, okay, that I think hopefully you'll find it to be interesting. So that has to do with Fibonacci and how Fibonacci's numbers, Fibonacci's sequence, relates to rabbits and sunflowers. Okay, so everybody, not everybody, but the main introduction of Fibonacci is always through the rabbit problem. So here's a drawing of a man, Leonardo of Pisa, Leonardo Pisano Bigolo. He lived a long time ago, right? It's like 800, 900 years ago. Okay, so that's Fibonacci. If you go on the web, you find this picture of him everywhere, right? Don't believe everything you see on the internet. If you go a little bit further, they'll say there's actually no known drawings of him or pictures of him. So someone drew this of him maybe 300 years after he lived or something, okay? But it's a nice picture anyway. Okay, so let's start talking about the rabbits. Okay, so he's very famous for this problem of rabbits. Okay? So what is the problem? This is the Fibonacci's rabbits problem. So a man put a pair, right, a male-female pair, so they can reproduce. A man put a pair of newly born rabbits in a field, a closed field. And then there are certain conditions. So the rabbits take a month to mature before mating, right? So they're newly born. Then they take a month to become adults. Then the rabbits mate. And then it takes 1 month after mating before the females can give birth to another pair of rabbits, another pair of male-female rabbits, okay? And then immediately they mate again. The adult rabbits mate again. And the young ones grow up, become adults, and then they mate, and so on, okay? So we assume this is a mathematical problem. It has nothing to do with real rabbits. But it's a well-posed mathematical problem. We assume that no rabbits die. And then the question is, how many rabbit pairs are there after 1 year? Okay, after 1 year. You guys can take seats. Okay, so that's the famous Fibonacci rabbit problem. Okay? So let's set up a solution. So I'll do it through a table. So the top row of the table is the month. Right? January, February, March, April, May, June, July, August, September, October, November, December, back to January. And then I'm going to fill in this table with the number of rabbit pairs. Okay? So these are the number of newborn rabbit pairs, juveniles. These are the number of adult rabbit pairs. And then this is the total, the sum of the juvenile and the adult. Okay? So we start off with 1 newborn pair of rabbits on January 1st. Okay? So we're going to write down the number on the first of the month. So on January 1st, we have a newborn pair, no adults, right? So one rabbit, one pair of rabbits. Okay, 1 month goes by, February 1st. The juveniles mature to an adult. It takes 1 month for a newborn rabbit to become an adult. Okay. Still only one pair of rabbits. Okay. 1 more month goes by. So what happens? So this, in February, they were 1 month old, so the rabbit pair mated, right? The female rabbit became pregnant for 1 month. And then on March 1st, gave birth to a new born pair of rabbits. Okay? So this pair of adult rabbits, the female, after 1 month of pregnancy, gave birth to a newborn pair. And this adult pair of rabbits is still an adult pair of rabbits, right? Nobody dies. No rabbits dies. So now there are 2 rabbits. Okay? So what happens after 1 month? This newborn will become an adult. These adults will stay adults. So we should have 2 adult pairs of rabbits, right? And then these adult pairs mated again, right? The original rabbit pair mated again and gave birth to another pair of newborn rabbits. Okay, so we should have 1 juvenile here from this one giving birth, and we should have 2 adults here from this one becoming this pair becoming an adult and the adult pair that was already there. Okay, so 1, 2, and 3. So 3 total rabbits now. So we have 1 rabbit, one rabbit pair, 1 rabbit pair, 2 rabbit pairs, 3 rabbit pairs, and so on. Okay? So everyone understands how this table is being built up. Okay? Any questions about the table? Okay. And then what's the answer? So how many rabbit pairs are there after 1 year? So we're to January 1st here. So there's 233. Okay? So we've gone from 1 newborn pair of rabbits to 233 pairs of rabbits. Okay? So that's the Fibonacci problem posed 800 or so years ago. Okay? The internet says that it actually comes from an even earlier problem that he just copied the problem, essentially. But in any case, it was famous for Fibonacci because it was in his famous book that he had written at that time. Okay? So this is called, hello? This is called the Fibonacci sequence, this bottom line. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233. You can see where this comes from. This number 2 comes from 1 plus 1. This number 3 comes from 1 plus 2. 5 comes from 2 plus 3. 8 comes from 3 plus 5. 13 from 5 plus 8, right? And so on. So that's how you construct the Fibonacci sequence. Okay? We can write down the mathematics. Okay? So if these are the A numbers, starting with A1, A2, A3, A4, then AN plus 1 comes from AN plus AN minus 1, right? A5 comes from A4 plus A3. So that's the mathematical expression of the Fibonacci sequence. This equation by itself is not complete because you need to start somewhere, right? So you cannot get A1 because that would be A0 plus A minus 1. But there is no A0 and A minus 1. There's only A1 and A2, right? So you have to specify the initial conditions of this equation. So the initial conditions are A1 is 1, A2 is 1. Okay? You cannot get A1 and A2 from a difference equation that looks like this. You have to specify it. Okay? Just out of curiosity, raise your hand if you've seen the Fibonacci sequence before. Seen the Fibonacci sequence before? Seen it? Okay, very nice. Okay, Fibonacci, it's as easy as 1, 1, 2, 3. Do you get this joke? I don't know. This is an English joke. So maybe, do you know there's an expression in English? Something is as easy as 1, 2, 3. So this is a joke on that. I had a discussion with another professor, a Cantonese professor, whether you guys would get the joke or not. So I asked him if there's any expression is as easy as 1, 2, 3, and he said no. So I told him I would ruin the joke by explaining it. Okay, so let's solve the Fibonacci equation. You can actually solve it completely. So you can determine A sub n as a number. Okay, you can get a complete solution. I won't go through the mathematics to find the complete solution. But instead, I'll show you an approximate solution. Okay? So how do we get the approximate solution? So you start with the equation. Okay? It has initial conditions, but we won't need the initial conditions to find the approximate solution. Okay? So what I want to do is I want to get a feeling or a solution to this equation when n is very large. Okay? When n is very large. So to do that, I'm going to first divide both sides of this equation by A sub n. Okay? So we divide through by A sub n. So we get the left-hand side. A sub n divided by A sub n is 1. And A sub n minus 1 divided by A sub n. Okay? Then what I'm going to look for the solution is to look at the ratio, the limit of the ratio when n is very large. Okay? So we say when n is large, we write that as the limit as n goes to infinity, right? You guys know that mathematics, I think. Of an plus 1 over a sub n. And that's going to be a number which we're going to call phi. That's a capital Greek letter, phi. Okay? So we're going to take the limit as n goes to infinity of this equation. So the left-hand side is exactly what I wrote here. So that will become phi. Okay? Phi equals 1 plus, and then what is this thing? This thing is the reciprocal of a sub n divided by a sub n minus 1, right? So it's the larger one divided by the smaller one in the sequence, but the reciprocal of that. And n goes to infinity, so it doesn't matter whether this is an plus 1 over an, or this is an over an minus 1, or this is an minus 2 over an minus 3. It's the same number, right? N goes to infinity. Okay. So the Fibonacci equation becomes phi equals 1 plus 1 over phi. Okay. So we get an equation for phi, right? Okay. What is that equation? Well, we can multiply both sides by phi, put everything on one side, and we get a nice quadratic equation, right? Phi squared minus phi minus 1 equals 0. OK. The roots are negative b plus or minus the square root of b squared minus 4ac over 2a, right? There's two roots of the equation, but we only care about the positive one because the Fibonacci numbers are all positive. So there's our phi, 1 plus root 5 over 2. OK? That's called the golden ratio. OK, raise your hand if you've seen phi before. Have you seen that number before? OK. Raise your hand if you've seen pi. All right. So that means that your hand is alive. Raise your hand if you've seen E. Do you know E? OK. So phi is one of those numbers, you know. Pi, E. Pi and E are special because are slightly different than phi because they're called transcendental numbers. They're not the roots of a polynomial equation with integer coefficients. Okay? But phi is not a transcendental number, but it's an irrational number, right? It's an irrational number, but very interesting number. Okay? So the golden ratio. We have this equation, phi is equal to 1 plus 1 over phi. Okay? So let's, the golden ratio, we can calculate it in a different way. Why is it called the golden ratio? It's the ratio of two Fibonacci numbers, but there's another way of defining the golden ratio. So we say two positive numbers, x and y, with x greater than y, so x is the bigger number, are said to be in the golden ratio if the ratio between the sum of those numbers, x plus y, and the larger one, x, so x plus y divided by x, is the same as the ratio between the larger one, x, and the smaller one, y, so x over y. So x plus y divided by x is equal to x over y. Then x and y are said to be in the golden ratio. Okay? So there's the equation. Y over x equals x over y. X and y are said to be in the golden ratio. So x and y is this phi. Okay? Phi is the golden ratio. So when you substitute in x over y equals phi, you get the same equation as the Fibonacci number equation. Phi equals 1 plus 1 over phi. Okay? So that's another definition of the golden ratio of phi. Okay? So from the golden ratio, you can construct the golden rectangle. The golden rectangle has side lengths in the golden ratio, 1 to phi, 1 to phi. The nice thing about the golden rectangle is when you remove a square, what remains is also a golden rectangle. So here it is. That's the golden rectangle. This is length 1. This is length phi. Okay? So this is 1 to phi. Here's a square. So this is 1, right? But phi is equal to 1 plus 1 over phi. So this is 1. So this is 1 over phi, 1 over phi. This height is 1. So this is 1 to 1 over phi. Or if you multiply both by phi, this is 1 to phi, right? 1 to 1 over phi is the same thing as phi to 1, right? So this is also a golden rectangle. And then you make this a square again. So this is a golden rectangle. You make this a square. So this one is a golden rectangle. This is the square. So this is a golden rectangle. This is a square, so this is a golden rectangle, and so on and so on. Okay? So it's kind of a cool object. Because of that relationship, right? Phi is equal to 1 plus 1 over phi. Okay? And then this is the spiral associated with that object. That's a logarithmic spiral. Okay. I need to do some mathematics, introduce a new mathematical concept here. So this is the concept of a continued fraction expansion. So this is an algorithm to write an irrational number x as what's called a continued fraction. Continued fraction. So x is some number. So we write it as an integer plus 1 divided by an integer plus 1 divided by an integer plus 1 divided by an integer to infinity. Okay? This is an irrational number, so it has no representation as an integer divided by an integer. Okay? So it has to be infinite here. And the algorithm for constructing this continued fraction expansion is that every time you add an n, you're bracketing x. So when you add an n, you're larger than x. You add another n, you're smaller than x. Then you're larger than x. Then you're smaller than x. Then you're larger than x. Then you're smaller than x. But you're getting closer and closer to x. Okay? So you're limiting x by becoming larger, smaller, larger, smaller, larger, smaller. And there's an algorithm for doing that. That means I can tell you a method to do that for any irrational number. Okay? So how about pi? Everybody knows pi. Here's pi. Okay? So this is the continued fraction expansion for pi. So we can look at approximations to pi. So the first one is 3 plus 1 over 7. So 21 over 7 plus 1 over 7 is 22 over 7, right? So that's the first one. 3.14. Okay. The next one, you include the 15, right? You include the 15. 3.1415. Okay. And so on. Right? So what about phi? So this is where phi becomes a very interesting number. Okay? The golden ratio. How does phi work? Well, I can show you how to construct the continued fraction expansion of phi. Because we know phi equals 1 plus 1 over phi, right? Then if you're clever, really clever if you haven't seen this before, mildly clever if you've seen something like this before, you take this phi here and you put in 1 plus 1 over phi, right? So phi is equal to 1 plus 1 over phi. So this phi here is equal to 1 plus 1 over phi, right? So this equation is true. Then you take this phi here, and you put in 1 plus 1 over phi. Okay? This is a continued fraction expansion. And you keep doing that forever, right? So it never ends. 1. This is n1, n2, n3, 1, 1, 1. 1, 1, 1, 1, 1, 1, 1, right? It's all ones all the way down. The partial fraction expansion has all ones. Very special number, right? So we say that phi is the most irrational number. The most irrational number. Here are the partial fraction expansions. 1, 2, 3, 5, 8, 13. That's the Fibonacci sequence, if you don't remember. Okay, so this is the ratio of the neighboring Fibonacci numbers. So we said that this converges to phi, right? This converges very slowly, has the slowest converging continued fraction expansion. So that's why we call phi the most irrational number. It's the most difficult number to represent as a rational number. Okay? So we need to know that to understand the sunflower. So this is the sunflower, right? This is a field of sunflowers. Those are the very big flowers, right? OK, so here's a Fibonacci sunflower. This is the head. OK? When you look at this head, what do you see? You see spirals, right? Here's spirals. But then if you look the other direction, oh, here's spirals too, right? You have spirals going this way, counterclockwise. And you also have spirals going this way, clockwise, right? OK, so as a scientist, what do you want to do? Count the spirals. I do this in my class. I actually count them. 1, 2, 3, 4, 5, 6, 7. I can't do that here. I need to have I project it on the whiteboard, and I draw the spirals, and I number them, and we count them. Okay? Takes about 10 minutes. But it's good because it shows you experimental experiments, right? It's possible for a mathematician to do experiments. So here's the count. 21 and 34. So 34 going clockwise, 21 going counterclockwise. Those are two Fibonacci numbers, right? This is the Fibonacci sequence, 21 and 34. OK? Here's another one I took from the web, the internet. You count these spirals, 34 and 55. 34 and 55. These two Fibonacci numbers. OK? So why are there Fibonacci numbers in the sunflower? OK, that's the question. Why are the two numbers from the Fibonacci sequence in the spirals of the sunflower? OK, so I'm going to make a model of a sunflower, the growth of a sunflower head, OK? To try to give you an explanation of why we're getting Fibonacci numbers in the counts of the spirals. Okay. So it's a very simple model, just to get the main idea across. Okay. So we assume the sunflower head starts small and is growing, right? So the florets, the ones that we were counting in the spirals, the florets are created at the center of the sunflower, okay, constantly being created at the center and then moving out as the sunflower head grows. When the floret is created at the center, we assume that it will move out radially in the sunflower. So if it's created at the center, it will move out radially as the sunflower grows. Okay, move out radially, radial direction. Okay? And furthermore, each new floret is rotated through a constant angle before moving radially. So the first one is created, is moved out, right? Starts to move out as the sunflower head grows. Then the second one is created. There's an angle, and then it will move out. Third one is created. There's an angle, and then it will move out. Okay? I'll show you that later. Let's denote the angle by 2 pi alpha. So alpha is between 0 and 1. So alpha equals 0 is no rotation. Alpha equals 1 is a rotate around the whole circle. Actually, no rotation because you get back where you are. Okay? So you have intermediate rotation angles. OK, so let's look at alpha equals 1/3. So this is a MATLAB simulation. So this is a simulation of this model. OK? So these are the three first Florays that were created, right? So the first one was created, and then it's going to be moving out radially. The second one is created here, right, after rotating an angle 1/3 of the full circle, and then it will be moving out radially. The third one is created here, and then it will be moving out radially. Okay? That's what the model says. And then the fourth one is created. This is the fourth one here, created down here, and then it moves out radially, and so on. Okay? So I'm trying to model the sunflower head, right? 3 straight lines doesn't look like a sunflower head. Okay? Right? So this is alpha equals 1/3. So let's consider alpha rational. So 1/3 is rational. Let's try another rational number. Here's 3/5. Okay? How is this being created? So we have created here, and then we rotate 3/5 of a circle. 1, 2, 3 here. Then 3/5 again. 1, 2, 3 here. 1, 2, 3 here. 1, 2, 3 here. 1, 2, 3 back again here, right? So 5 in the denominator means 5 arms. 1, 2, 3, 4, 5. So after 5 florets are created, we go back to the starting point. Okay? So any rational number down here will have lines, right? Depending on the denominator of the rational number. Okay? So what do you need to get rid of lines? You need an irrational number, right? So an irrational number is not represented as an integer divided by an integer. So there's no way to get back to where you start, right? No way to get back to where you start. So what happens if alpha is irrational? So you will never get back to where you start, so you won't get lines. Okay, won't get lines. So how about pi? So that's the number everybody knows, right? So let's set alpha to be pi minus 3. So it's the fractional part of pi. Okay? 0.14, whatever. Okay? And let's do the simulation on the computer of the model. So what do you think this will look like? You're never going to get back to where you started, right? So what do you think it will look like? Okay, take a guess in your mind. Let's see what the simulation tells us. Raise your hand if you guessed that. Not that easy, huh? We get spirals. We get spirals. 1, 2. I can count this, right? Not too many. 1, 2, 3, 4, 5, 6, 7 spirals, right? 7 spirals. They're going counterclockwise, right? 7 spirals. Okay. Why do we get 7 spirals? 22 over 7. Remember our continued fraction expansion? Pi can be represented by 22 divided by 7. So pi minus 3 is 1/7, 7 spirals. Right? If it was actually 22 over 7, we would get 7 lines. Instead, we're getting 7 spirals. Because pi minus 3 is less than 1/7, right? It's just an approximation. Pi over 3 is 1/7. We're getting counterclockwise spirals. So why is that? So the first floret that's created moves out radially. That's this one here. That's the first one created. Okay? And then we go around, create 6 more. Then we come back to here. 22 over 7 is less than pi. So we don't quite go back to the line, right? We're short of that line. So this one is dropped down a little bit. This one here is dropped down a little bit. Because the angle it's coming out now is an angle that's slightly negative, right? And then this one gets dropped down a little bit more. So they all get dropped down a little bit. So if you draw the line from the origin to these points, they're all having slightly dropped down angles, okay? Because you don't make it back. And the net result is a spiral. Okay, the net result is a spiral. Okay? So what about our most irrational number? Okay, remember, phi is the most irrational number. Here we go. Pretty nice, right? What do we get? Spirals. Oh, spirals, both directions. Right? Spirals, both directions. Because phi is represented by the ratio of 2 Fibonacci numbers. One pair is larger than phi. The neighboring pair is smaller than phi. So those 2 pairs give you spirals in 2 different directions, right? And the denominators of those 2 pairs are 2 consecutive Fibonacci numbers. 2 consecutive Fibonacci numbers. So here are 2 simulations. This one has 13 and 21 spirals. This one has 21 and 34 spirals. So those are what we saw in those 2 sunflowers. Okay? That's what we saw in those 2 sunflowers. So there is a simple model which tells you how, because phi is the most irrational number, how you might expect it to show up in nature when you want to put, when there's some forces that are putting these florets, compacting these florets in the head of the sunflower, right? Okay. You also see this in pine cones. These are the spirals. And then man-made objects. If you look at the web, there's a lot of fun things out there. Not all of it true, but fun nevertheless. This is the Parthenon. You know, there's a claim that this golden rectangle is a very pleasing geometrical shape. And there's the head of Mona Lisa with a golden rectangle on it. Okay, thank you.